Technical report for free vibration test of elevated water tank. This is the example, you will see it. Introduction. The free vibration test is conducted on the empty elevated water tank, and you see the water tank somewhere here. Empty elevated water tank. To evaluate its dynamic properties, the tank is laterally displaced by a cable applying a force, then released to vibrate freely. Measurements of the vibration amplitude, decay, and time period enable the determination of stiffness and damping factor and natural frequency, weight, damping coefficient, number of cycles before vibration diminishes to a certain amplitude. All these things we will find it out. Experiment data. Applied force is 144 Newton, 144,000 Newton, and initial displacement is 0.05, and amplitude after 5 cycles is 0.035 centimeter, and the time for 5 cycles is 2 seconds. So after 5 cycles, this is the amplitude. Initial amplitude 0.05. So say 50 centimeter, then it becomes 35 centimeter after 5 cycles. Introducing, right? So it takes 5 cycles to complete 2 seconds. So we know how to calculate the stiffness. By Hooke's law, we know for stiffness is force by displacement. This is the force and this is the displacement. So displacement is stiffness known. So damping factor, we can calculate the damped period for T5 is 2 second and 5 cycles. So per cycle is 0.4 second. Calculate the logarithmic decrement. So logarithmic, the amplitude of first one is 0.05. After 5 cycles, the amplitude is 0.035. That's why we are dividing it by 5. So it becomes 0.0713. That's the delta value. So damping ratio, we know 2 pi by delta equal to square root of 1 minus eta squared. So this is approximately delta equal to eta equal to delta by 2 pi. So we are getting this much, and this becomes 1.136%. Undamped natural frequency, we know. To damped natural frequency, we will calculate this one, and then damped natural frequency to undamped, this is a relation. Then from here we can calculate the natural frequency. Undamped natural frequency, it's going to be 15.709. so these two are almost close. So damping is small, that's why these two are almost close. So we can calculate mass and weight. So natural frequency square root of k by m. From that, m is k by omega squared. So this is the mass. Then weight we can multiply by g, and we are getting the weight. Damping coefficient c is equal to 2 into m into omega n. This is the damping coefficient. And actual damping coefficient equal to this value. So number of cycles, n, amplitude reduce 0.005. So we just wanted to find after how many cycles is going to reduce 0.005. So natural logarithm equal to u naught by un by n into theta. So n equal to this value 0.05 to last is 0.005 by delta. It becomes almost 32 cycles. So it takes 32 cycles. That tank with water tank is there, right? That's going to vibrate almost 32 cycles just to go from 0.05 meter to 0.005 meter. That means what? It's a 5 centimeter to 5 mm. So summary of results: stiffness we have known, damping factor, undamped natural frequency, mass, weight, damping coefficient, number of cycles to reduce to the 0.005 amplitude, 32 cycles. So physical interpretation, if you see it, stiffness is a measure of the tank's resistance to lateral displacement. Damping ratio is very small, indicating it's a under-damped system. Natural frequency defines inherent oscillation without damping. Weight, that we can get it from the mass, and damping coefficient we can get it, and then 32 cycles takes are needed for the amplitude to decay from 0.05 meter to 0.005 meter due to damping. So we can have a group discussion, like we applied lateral force of this much and displace the tank by 0.05 meter. What's the stiffness? Stiffness is just a force divided by the displacement. So we can get this as the stiffness value. Now after releasing the tank, we record vibrations. 5 cycles took 2 seconds. What's the period? So 5 cycles took 2 seconds. So the period for per cycle is 0.4 seconds. The amplitude dropped from 0.05 to 0.035 after 5 cycles. How do we find the damping? So we calculate a logarithmic decrement. That's 1 divided by 5 into natural logarithm of 0.05 to 0.0035 for 5 cycles. That's why 1 by 5 we are putting it. Otherwise, it's simply natural logarithm by 0.05 0.035 between successive two vibrations, but it takes 5 cycles. What value do you get? It's a 0.073. Good. How is damping ratio? Eta is related to the logarithmic decrement. Damping ratio is nothing but logarithmic decrement divided by 2 pi. So roughly it's 1.13%. Perfect. What's the damped natural frequency? We can calculate damped natural frequency. And how do we get the undamped natural frequency? Using this relation. That's almost 15.7. Both are almost equal. And how do we find the mass? From natural frequency we can get the mass. What's the value? It's 11,680. So good. What about the weight? We can multiply by gravity. Multiply mass by gravity. And exactly now how to find the critical damping coefficient? We have this C is equal to into m into omega n. Calculate it. So this is the value. Finally, actual damping we can multiply by rho. Cc multiplied by rho. This is actual damping. So how many cycles per amplitude to reduce 0.05? Using n equal to natural logarithm of 0.05 0.005 divided by delta. That's 32 cycles. You understood the whole problem well. Can we try one more with the damping next? We will add a complexity step by step. Okay team, we performed a free vibration test on water tank. The cable applied a lateral force of 144 kN, displacing the tank by 0.05 meters. The cable was cut. We recorded the vibration. After 5 seconds, amplitude decreased from 0.035 meter. It was time taken was 2 seconds. Let's analyze step by step. The first question is, how do we find the stiffness from this data? Stiffness is the force divided by the displacement, and it tells us how much force is needed to cause a unit displacement. So stiffness is like a spring constant for the tank's lateral motion. I think of it like a big spring resisting the lateral force. And we know 5 seconds took 2 seconds. So what does this tell us? So each cycle it takes 0.4 seconds. Period of damped oscillation. Why do we call it damped? Because amplitude decreases over time due to damping, energy loss, friction, material damping, and so on. So speaking of the amplitude, it dropped from 0.05 to 0.005 in 5 cycles. How do we find this? How do we use this to find damping? We use logarithmic decrement, which measures the rate of amplitude decay. Logarithmic decrement, which measures the rate of amplitude decay. And so this is the formula, so we can get it. Natural logarithm of amplitude ratios. We use logarithmic decrement as just a percentage of decay. Because vibrations decay is exponential, logarithmic decrement linearizes. It makes the calculation easier. How does this relate to the damping ratio? The damping ratio, we know this is the formula for damping ratio. We can calculate it's about to be 1.14 percentage. So delta tells us how damped. This is just a very under damping. It's a damping ratio is very less. That's why it tells how damped the system is compared to the critical damping. Precisely, if eta equal to 1 means critically damped, no oscillations. Our value is 0.0. Instead of 1, it becomes 0.011. That means 1%. It's very lightly damped. So what is the natural frequency? The damped natural frequency, we can get it from the undamped natural frequency. We can get using this relation. These two are almost equal because theta is small. Why do we care about the undamped frequency? Because that's the natural oscillation of the system without any energy loss. Fundamental property of the design. Can we use omega n to find the tank's mass? Yes, we can use omega n to find the tank mass. So this is going to be the tank mass. And that's the effective mass causing the lateral vibrations. Mass includes the tank structure and any fluid or attachment conductive inertia. How the weight? This is the weight we can calculate. How do we find the damping coefficient? We can calculate the critical damping coefficient. After that, we can find out the actual damping coefficient. What is the damping coefficient physically represent? It's a viscous damping force proportional to the velocity, resisting motion and dissipating energy. So first question, how many cycles? Final question, how many cycles before amplitude is to 0.005? We can use this natural logarithm and logarithmic decrement to find out the number of cycles. So the tank will keep vibrating for quite a while before the vibrations are negligible. That's typically lightly damped structures. Why does the damping matter in the design? Because damping controls how quickly the vibrations die out. If we don't know the damping, we cannot find out easily whether it's quickly dying out or not. See, because of the damping, once we know the damping and logarithmic decrement, we come to know how many cycles it takes for the vibrations to die down or vibrations to go to a very small negligible amount of amplitude. So a lot Low damping means long-lasting vibrations, which can cause fatigue. Low damping means long-lasting vibrations. Can we increase the damping? Yes, through the design features like dampers, braces, material choice. How accurate is this method? Pretty good for linear small vibrations. For larger, non-linear, bigger, more complex is needed. So, alright team, today we are analyzing the free vibration test on an elevated water tank. The tank was laterally displaced by a cable, applying horizontal force, displacement of this much, and after we release, we observed vibrations. After 5 cycles, the amplitude dropped to 0.035 meter and the time elapsed was 2 seconds. We calculate the following: stiffness, damping ratio, undamped frequency, mass by damping coefficient, number of cycles for the amplitude to go to 0.005 meter. So we start with stiffness, right? That's the force over displacement. Exactly, it follows the Hooke's law. So the tank behaves like a spring with the stiffness of this one. This tank behaves like a spring. Correct. That's the lateral stiffness of the system. We know that the tank vibrated 5 cycles in 2 seconds. So what's the period? So damped period is 0.4 seconds. Undamped natural frequency is 15.708. Now damping. The amplitude dropped from 0.05 to 0.0035. That's exponential decay. Because of the exponential decay, the drops we can see it. And correct. The damped free vibration decays exponentially. We use logarithmic decrement. Using this formula, we can find out what's going to be the logarithmic decrement. And damping ratio is linked to the natural decrement by this formula. So we know how much is going to be the damping. That ratio is 1.14%. It's ideally it's going to be the underdamped. It's lightly damped, which compared to the one means critical damped. How do we calculate the undamped frequency? Undamped frequency, we have the ratio with respect to damping ratio. So since the damping ratio is small, we know Wn, undamped and damped frequencies are going to be almost equal. Can we now find the mass of the tank using omega and k? Yes, of course we know the omega n and mass in k. So from this mass we can come to know. And to find out the weight, we will simply multiply with the gravity and always check the units. Next, the damping coefficient. How can we find out the damping coefficient? That's 2m into omega n. So from this we can find out the damping coefficient and the actual damping. This is the critical damping. Cc is the critical damping coefficient. So the system has a damping proportional to the velocity of 4.16. Precisely is discussed damping. How many cycles for the amplitude to drop? This is the 33 cycles. So even with a small damping, it takes 33 cycles to reduce. Even with the small damping, 33 number of cycles it takes. That's the effect of low damping. Vibration persists for many cycles. So if the damping is very small, vibration is going to persist for long. If the damping is high, the vibration is not going to be lost forever. If the damping were higher, would it settle faster? Yes, of course. Higher damping ratio, faster decay, fewer cycles. Can we control damping in a water tank like this? Yes, we can add some dampers. So welcome back. Today's task, we are analyzing the free vibration test performed on an elevated water tank. We pull the tank, this force, displacement, cable cut. Once the cable gets cut, the tank is vibrating freely. After 5 cycles, amplitude drops. The time taken for the 5 cycles, 2 seconds. So we start with stiffness. The system acts like a linear spring, so we use Hooke's law. So this tells us how rigid the tank is against lateral force. It is higher the stiffness, more force is required for given displacement. How rigid the tank is against lateral forces. The tank vibrated 5 times in 2 seconds. So what's the period per cycle? It's a 0.4 second. From that we get the damped natural frequency. What does this tell us? It's rate of oscillation with damping, slightly less than the undamped frequency. Logarithmic decrement and damping ratio. How do you measure how fast the amplitude decays? Using this logarithmic decrement. So is that high or low? And that's low. Typical for tall circuits like tanks. It shows low energy dissipation per cycle. So the damping ratio comes next. For lightly damped structure, we can get delta by 2 pi. Very small. That's typical structure unless special dampers are added. Undamped natural frequency, we can get it from this. Mass and weight, we have the relation. Damping coefficients. We can get it from this value. Number of cycles for to reduce the amplitude to this much. How many cycles it take until amplitude is from 0.05 to 0.005? 33 cycles. So it will take 33 cycles to reach 1/10 of the original amplitude. That's correct, because damping is slow. The vibration persists over time, over many cycles. What does this tell us physically? The tank is very stiff, has low damping. It is common in steel structures. Small disturbances may cause vibrations that last for many seconds. Engineer must ensure these vibrations do not resonate, become unstable during earthquakes or wind loads. So adding damping devices helps. Tuned mass dampers, basal isolations, amplitude foster. This harness assumes linear behavior, right? For small displacements, vibration theory is linear vibrations valid. Large motions, we would need nonlinear dynamic analysis. So, welcome everyone. You are all here because you have shown strong interest in vibration structural behavior. Today we will analyze real data from the free vibration test on a steel elevated water tank. Here's what we did. The tank was displaced laterally by pulling a steel cable, and force was this much, and displacement. See, the tank is like this, okay? And cable is tied like this. So from the original position, it displaced by 0.05 meter. So the force is applied to the cable 144 kilonewton. It's displaced, okay? Once you cut this one, because of this one, it's going to vibrate like this. So we know the tank stiffness. This is the stiff, right? Once you apply this much force, this much displacement is happening. So we know the stiffness. Well, to calculate the stiffness, only this force in the cable and how much it's displacing, actually these two are required, okay? So we cut the cable suddenly and let the tank vibrate freely. Amplitude reduced to this 0.05 becomes 0.035, because every time it vibrates, after some time it will stop, right, vibration because of damping. So after 5 cycles it becomes 0.035, and it takes 5 cycles to complete. It takes 2 seconds to complete the 5 cycles. So we will find out all these things: stiffness, damping ratio, natural frequency, mass by damping coefficient, cycles needed for the amplitude reduced to 0.005. So stiffness. Should we start with stiffness? Yes, from Hooke's law we know force into displacement is the force equal to stiffness in displacement. So stiffness equal to force divided by displacement. We know the stiffness. That's a huge stiffness. That's experienced tank structure. It has a wide base frame. This stiffness reflects the lateral resistance, not vertical, because laterally displaced, right? So this is the lateral stiffness, not the vertical stiffness. Oscillation period, the rhythm of the tank. We observe 5 cycles in 2 seconds. So that gives us the period. So 1 cycle it takes 2 divided by 5. So 0.4 seconds. Undamped natural frequency. So this is the natural period. So 1 divided by period, that will be the frequency. Then we will get to multiply by 2 pi, then radians per second. That's the frequency of oscillation with damping involved. So logarithmic decrement, how fast do we fade? How fast is that going to fade? We know amplitude drops from 0.05 to 0.035 in 5 cycles. How do we calculate the damping? That's where logarithmic increment comes in. So this is logarithmic increment, number of cycles 5, initial displacement, final displacement over 5 cycles. So this is logarithmic decrement. So the damping causes the amplitude decay. Damping causes the amplitude decay exponentially, right? So that's where the amplitude after n cycles is un equal to u naught e power minus n logarithmic decrement. So damping ratio, how lightly the damped it is it? How does this connect to the damping ratio? Delta is connected to the 2 pi rho. So from that we will come to know what is the damping ratio. Just 1.153%. That's very low. Yes, tanks, tower bridges are lightly damped. This matters because they will vibrate longer. If this damping ratio is less, that means what? They are going to vibrate longer. Then undamped natural frequency, that's pure oscillation without damping. What's undamped natural frequency then? Use this relation. This is the undamped frequency. So damping does not change the frequency much because it's very less. Unless damping is high, in most buildings the difference between omega and omega d is negligible. Mass and weight. Knowing what moves can we find the mass from this undamped natural frequency? Yes, rearrange the equation, you can get the mass. So the effective mass is 11 tons. Now for weight and damping coefficient, resist the motion. Can we now compute the damping coefficient? First compute the critical damping, then damping, actual damping. This tells us the force plus also the velocity, right? So yes, damping force is damping coefficient into velocity. So if the amplitude goes from 0.05 to 0.005, how many cycles it take? It takes 33 cycles. So over 33 cycles, 90% of motion is lost over 30 cycles. That's why damping is so important. In real life, we don't want vibrations to linger. These are the results. Final. What if the tank was full of water? The mass would increase, that would reduce the natural frequency. Also, fluid interaction would introduce nonlinear damping. Can we simulate that? In the next section, we can see it.